Dear students, we will discuss today about the introduction of nonlinear systems. There is no general method for dealing with all nonlinear systems because nonlinear differential equations are very virtually divided to a general method of attachment. Exact solutions can be found only for certain simple nonlinear differential equations. For many nonlinear differential equations of practical importance only, approximate solutions are possible, and these solutions held true only under the limited conditions for which they are obtained. Because there is no general approach, we may take up each nonlinear equation or group of similar equations individually and attempt to develop a method of analysis which will be satisfactorily applied to the practical group. One way to analyze and design a particular group of nonlinear control system in which the degree of nonlinearity is small is to use equivalent linearization technique and to solve the resultant linearized problem. The describing function method is one of the equivalent linearization method. The describing function method enables to study the stability of many simple nonlinear control systems from a frequency domain point of view. This method provides stability information for a system of any order, but it will not give exact information as the time response characteristics. In other words, the analysis of nonlinear control system which may be highly nonlinear include the solution of the actual or simplified nonlinear differential equation by phase plan technique and the second method of Lyapunov. The phase plan method provides information on both stability and the time response behavior, but it is limited to first and second order systems. The second method of Lyapunov may be applied to stability analysis of any nonlinear system, but its application may be hampered because of difficulties of finding Lyapunov function for complicated nonlinear systems. Now, classification of physical nonlinearities. Now, nonlinearities can be classified in two manners. One is inherent nonlinearity and intentional nonlinearity. Now, in case of inherent nonlinearity, these are unavoidable or inherently present in a system. That means whatever the system nonlinearity is present, that is permanently present in a system. So there is not regarding for anything to make input to the system to make it nonlinear. So it is already mentioned, already present in a system. So under which we have different parts like saturation, friction, then dead zone, on-off, backlash, and combinational nonlinearity. Now, what do you mean by saturation? We know that all practical systems, when driven by sufficiently large signals, exhibits the phenomenon of saturation due to limitation in physical capabilities of their components. For a system, a small input produces a linear output, but when the input exceeds a limit, the output becomes constant and gets saturated. For example, amplifiers and motors. Like in the second point, friction also. Whenever a mechanical surface comes in contact, a retarding force acts on the system, called viscous friction. It is linear in nature. In addition to the viscous friction, two other frictional forces act on the system, which are nonlinear in nature. One is Coulomb friction, which remains constant, and the other is friction, which acts during the starting the motion of the objects. So this kind of thing, this kind of frictional nonlinearity is very common in railway tracks. When the train starts in motion or it starts in gradient, up and down gradient, okay, it decreases as the velocity increases. Another inherent nonlinear phenomenon is dead zone. Now, what is the dead zone? That some system produces output only when the input crosses a particular limit. So when within the limit the output remains zero, that means whenever you give some input in positive input or in some negative input, the output remains zero.